For decades, the pharmaceutical industry tested gamma secretase inhibitors like semagacistat to halt Alzheimer's disease. These drugs were designed to block the enzyme responsible for creating amyloid beta. They failed in late-stage trials. Patients taking the inhibitors performed worse on cognitive and daily function metrics than those on placebo. The drug actively accelerated their decline. Compare that outcome to the Clarity AD trials for lecanemab. This presentation slide shows the trial data, highlighted by a highly significant p-value of 0.00005, confirming a 27% slowing of clinical decline compared to placebo. This specific antibody treatment is now on the market as Leqembi. Instead of blocking the enzyme upstream, it simply clears out the amyloid beta plaques that have already formed in the brain. These two trial outcomes create a strict pharmacological contradiction. The drug that blocked the enzyme, supposedly producing the toxic amyloid poison, actively harmed patients. But the antibody that merely swept up the downstream product provided a measurable, albeit modest, benefit. If the enzyme was truly a hyperactive poison maker, shutting it off would have helped. The fact that shutting it down caused cognitive harm indicates the field's foundational premise: an overactive enzyme is upside down. In biochemistry, the efficiency of an enzyme is defined by the rate at which it converts a substrate into a product. Producing 3 units of product instead of 1 only means the enzyme is overactive if the available substrate remained constant. If those 3 units came from 5 units of substrate, the enzyme has actually become less efficient. This diagram shows the canonical model of Alzheimer's, which relied entirely on measuring the product. Researchers found more amyloid beta and concluded that gamma secretase was overactive, churning out toxic plaques. The Area-Gómez program argues the field measured the wrong quantity. We must measure the ratio of amyloid beta to its uncut precursor molecule, C99. By that metric, gamma secretase in Alzheimer's tissue is severely impaired. The primary abnormality is a failing enzyme and the subsequent accumulation of its uncut substrate. Independent laboratories have corroborated this relocation of the pathogenic species. An expansive isogenic panel of human-induced pluripotent stem cell neurons proved that the early endosomal pathology seen in familial Alzheimer's is driven entirely by the beta-carboxy terminal fragments, like C99, and not by amyloid beta. The amyloid plaque is a partial record of a chemical cut that increasingly fails to happen. The disease is driven by the accumulation of the uncut upstream substrate, leaving a critical homeostatic signal running indefinitely. Before 2009, the physical location of the pre-senilin proteins, the catalytic core of gamma secretase, was an open embarrassment. Literature reported them scattered across the endoplasmic reticulum, the Golgi apparatus, endosomes, and lysosomes. This apparent promiscuity was a methodological artifact. When a protein is highly concentrated at a physical contact point between 2 structures, standard subcellular fractionation will cause it to report into every fraction that the contact touches. Pinning the localization to the interface resolves the confusion. The amyloid machinery lives at the mitochondria-associated ER membrane, or MAM. This is not a distinct organelle, but a transient structural apposition, a functional zone where the ER and mitochondria approach within tens of nanometers, held apart at a fixed distance by protein tethers. The MAM functions as a detergent-resistant, cholesterol and sphingolipid-enriched lipid raft. It is thicker, more rigid, and more ordered than the surrounding bilayer, making it the precise environment where presenilin 1 and presenilin 2 are heavily enriched. The enzymes whose mutations cause early-onset Alzheimer's are contact site proteins. They reside at the MAM because the chemistry of amyloid processing requires this specific, highly ordered lipid environment to function. The accumulating C99 substrate is not inert waste. Its transmembrane domain contains a highly flexible, defined surface that directly binds cholesterol. C99 is a biological cholesterol sensor. When plasma membrane cholesterol rises beyond a set point, the amyloid precursor protein is cut to form C99. C99 then migrates to the endoplasmic reticulum, where its affinity for cholesterol physically clusters the sterols into a rigid island, actively nucleating the MAM raft. This nucleation expands the platform and recruits cholesterol-handling enzymes, including ACOT1. These enzymes begin esterifying the excess sterol, damping down new cholesterol synthesis, and disposing of the excess into lipid droplets to restore the cell's equilibrium. Under normal physiology, Gamma secretase eventually cuts C99, dispersing the raft and ending the signal. In Alzheimer's disease, this cut fails. The uncut C99 remains locked in the membrane, driving continuous internal trafficking of cholesterol to an already expanded platform. The permanent upregulation of the contact site cascades into the mitochondria. Elevated C99 drives rapid sphingolipid turnover, which alters the lipid composition of the mitochondrial inner membrane. This specific lipid disruption physically impedes the assembly of the mitochondrial respiratory supercomplexes, starving the neuron of efficient energy production. Alzheimer's pathogenesis is a homeostatic control loop left permanently in the on position. The cell continually answers an alarm that has already been resolved, dying from the slow, crushing accumulation of an uncleared signal. The diagnostic standard for Alzheimer's biology is the exact ratio of the amyloid beta cleavage products, specifically the shift toward amyloid beta 42 over amyloid beta 40. The Area-Gómez program proposes a geometrical reading of this metric. The 42 to 40 ratio is a surrogate biomarker for the physical thickness of the lipid bilayer. Gamma secretase is an intramembrane protease that cuts based on the physical geometry of its engagement with the substrate. In a lipid raft of normal thickness, the C99 helix aligns vertically, matching the bilayer perfectly, and is cut at the 40 register. The expanded AMM domain activates contact-resident enzymes like ACSL4. This enzyme preferentially loads unsaturated fatty acid chains into the phospholipids. Because saturated chains are long and straight, and unsaturated chains are kinked, loading them in physically thins the membrane. Due to the physics of hydrophobic matching, the C99 substrate must tilt to accommodate the thinner bilayer. This physical tilt shifts its alignment with presenilin 1. The enzyme engages at a different angle, and the cut falls in the 42 register. If contact site dysfunction appears in ALS, Charcot-Marie-Tooth, and Alzheimer's, one must ask what makes these diseases distinct. The framework avoids the trap of generic biology by assigning specific directional values to each pathology. This data table illustrates the specific mechanistic assignments. Alzheimer's features increased contact function, driven by C99 and cholesterol. Conversely, wild-type alpha-synuclein is also a MAM protein, but its pathogenic mutations detach it from the contact. Parkinson's disease shows decreased contact function, driven by disruptions to phosphatidylserine. A generic model states that contact sites matter in neurodegeneration. A predictive, falsifiable biological framework assigns each disease a specific structural driver, a specific lipid class that fails, and a strict directional sign. The ultimate test of this predictive biology lies in the Colombian PSEN1 E280A kindred. Because this family carries a fully penetrant genetic mutation, the onset age of Alzheimer's is nearly guaranteed, allowing researchers to track the exact chronological sequence of the disease over decades. If Alzheimer's is driven by upstream lipid dysregulation, a signature should appear in the blood. Researchers found exactly that, a specific serum lipidomic signature defined heavily by ganglioside clearance deficits that cleanly separates asymptomatic mutation carriers from non-carriers. This timeline shows the true scale of the diagnostic failure. The lipid clearance deficits emerge in children between the ages of 6 and 12. This precedes the earliest established fluid biomarker of the disease, phosphorylated tau 217, by nearly a full decade. The pathogenesis begins decades before the first tangle forms and half a century before clinical diagnosis. The lipid dyshomeostasis is the upstream catalyst. This model successfully maps the field's dominant sporadic risk gene. ApoE4 containing lipoproteins are recycled inefficiently, driving intracellular cholesterol accumulation. The lipid rises. C99 rises in response to Uncleared, and the contact site is upregulated. Because the MAM is a vital physiological node for normal cellular cholesterol balance, we cannot simply sever it. Suppressing C99 below its normal functional range actively harms cognition. The therapeutic mandate is to tune the set point, not abolish the signal. This provides concrete pharmacological targets. Inhibiting ACSL4 or SOAT1 could intercept the specific enzymes responsible for thinning the membrane and esterifying the sterol pool, thereby restoring the proper geometry of the lipid raft without shutting down the entire pathway. By recognizing C99 as an active biological sensor and the uncleaved substrate as the primary cellular lesion, we relocate the origin of the disease. The solution requires repairing the feedback loop and intercepting the signal, restoring the cellular equilibrium long before the structural damage sets in.